Hey, this is Horner, and this is the first page of your work and energy multiple choice note sheet. For the very first thing, all we're doing here is just going through and listing some equations. So remember, potential energy due to gravity is just mass times gravity times the change in the height. The spring energy is really simple. That one's on your equation sheet. Also, 1/2 of the spring constant times the stretch squared. Kinetic energy is just 1/2 of mv squared. So those should have been really simple to do. The next one, they want us to start with the basic units and then convert everything, those units on over to joules. So for this one, we know mass is a kilogram, gravity is a meter per second squared, and then finally height is just a meter. At this point, we're going to end up with a kilogram times a meter squared over a second squared, which is really a Newton times a meter, and then that is just equal to a joule. For spring potential energy, we can ignore the half. The K is a Newton over a meter. We know x squared would be a meter squared, and so when you cross off one of the meters here, you end up with a Newton times a meter, and a Newton times a meter again is a joule. Kinetic energy is just a kilogram times a meter per, this one is a meter over, sorry, it's a meter squared over a second squared, which is again a Newton times a meter, and that is equal to a joule. For the next part, they want us to find the ratio of kinetic energy to final to kinetic energy original, and this is for the same mass objects. If I have this, I know that 1/2 of the mass times the velocity squared, and that's final velocity over 1/2 of the mass times the original velocity squared. So if this object has the same mass at the beginning and at the end, then we can cross off the halves, cross off the masses, and we're left with Vf squared over Vo squared, and that's the ratio then. So you don't have to worry about the mass nor the halves. For different mass objects, this changes a little bit. Our halves will cross off, and we'll be left with the mass of the object at the final position times the final velocity squared over the mass at the original position times the final velocity squared. It might be that it lost some mass. Maybe it's an airplane or a car, and it's burning fuel, so it gets rid of that. The next part of this review is basically just going through what mechanical energy is. So if it is constant total mechanical energy, so total mechanical energy, remember that's TME, is equal to the sum of all the energies. So it might be that you have kinetic energy plus potential energy due to gravity, okay? If I throw a ball up without any air friction, it will lose kinetic energy, and it will gain potential energy. On the way down, without any air friction, it will then go through. It will gain. On the way down, it will lose potential here, and it will gain kinetic energy. So you'll see that. So this is without any air friction. If something is a not constant mechanical energy, that means that the total mechanical energy is not equal to the sum of the potential plus the kinetic. And that's because you're losing a little bit of energy as you go through. So if you throw a ball up in the air and there's air friction, you're going to lose some kinetic energy, which is mechanical. You will gain potential, which is mechanical energy, and you will gain thermal energy, which means that it's going to lose some of this total mechanical due to this thermal energy. So we're going to call it ETH, but we're looking at that thermal energy as being something that's given off as heat. When the ball comes back down with air friction, it will lose, so here it will lose what potential it has gained, and it will have less kinetic energy than it started with. So we know that the rest of that energy is thermal. So that's the difference between constant, where you have conservative forces, where you don't lose any energy. So in the end, the total energy loss is 0. And then we have non-constant total mechanical energy, and that's where you lose energy due to thermal effects. That is page 1. Let's go ahead and take a look at the next page. So this is page 2. On page 2, they want us to just go through the spring force equation. We know spring force is equal to the spring constant times the compression. So here K is the constant. Remember, the constant is measured in newtons over meters. And if I have a graph that is force versus stretch, and I find the slope, it gives you K. So the slope gives you the K value. If I plot instead X versus F, and I get that straight line, then I actually have 1 over K is my slope. So this will give me 1 over K, and that's the difference between the two. For spring energy, we know spring energy from your equation sheets, just 1/2 of K times x squared. That's very similar to 1/2 mv squared, but notice instead of mass, you have K, and instead of velocity, we have position, or the stretch or the compression. Solving for speed of a block when it is pushed by a spring. So here we know that energy is conserved, and if energy is conserved, the energy in the spring is 1/2 K x squared, and that should be equal to 1/2 mv squared. So now what they want us to do is rearrange the equation for speed in this space that we have down below. I can see right off the bat that our 1/2s will cross off, so we're going to have kx squared is equal to mv squared. We're going to divide both sides by m, so now we have kx squared over m, and now we're going to solve for v. So when I solve for v, I'm going to take the square root of both sides, so that would be kx squared over m, but my x squared I can pull out of the radical, and I can make this x times the square root of k over m. So it's important that you know how to go through and modify a lot of these. For spring graphs, there are several spring graphs here that you need to kind of know what's happening on each one. In letter A, you'll see that I have a constant force, okay? But that constant force is producing just a constant stretch. So this is one that just continues to stretch with one weight applied, and it will just go forever, or it'll go until the spring can't stretch anymore. B is a spring that becomes more stiff as it is stretched. So some springs don't have a constant K value. They actually get bigger as time goes on, and so you'll see that here. Letter C is one that follows Hooke's law. It could also have a positive slope. So here it says draw C with a positive slope. So here's letter C with a positive slope. We have force and we have position. And if you did the absolute value of Kx, you'd end up with this. Then finally, the last one is a spring that begins to stretch normally, and then it's stretched too far, and when it gets stretched too far, all it does is it loses that springiness to it, and you just have one force that's able to stretch it out into infinity. And that is the second page. Let's go ahead and take a look at the third page. This one deals with pendulums and energy. So at the highest point on both ends, we see, even in this picture here, that all of the energy is UG, and remember that is called gravitational potential. At the lowest point, all of the energy here is kinetic, and so that's just kinetic, and so that's pretty simple. When we talk about, so that's really all you need to know on pendulums. For cars, trucks, and things that are braking, the distance to brake is proportional to the energy that that car truck has. So the more energy, the further the braking distance. And so here, equal energy, we have equal braking distance. If I have two cars, let's say I have a 2,500 kilogram car and a 5,000 kilogram truck, and they're both moving at 25 meters per second, and they both slam on their brakes to a skid, and the coefficient of the friction between the tires is 0.84, they want to know how far do they each take to stop. So we're going to use the equation kinetic energy is equal to the force of friction times that distance. For a car, we know that the equation for kinetic energy is equal to 1/2 mass times the velocity squared. and that's equal to the force of friction. Now remember, the force of friction for this is equal to mu times the normal force, and the normal force is just mg in this case because it's on a horizontal surface. Then we have the distance that it travels. The truck, same thing, 1/2 mv squared is equal to mu mgd. Notice that if I do put in the mass, it's 2,000 here and 2,000 here. This one would be 5,000 here and 5,000 here. But because we've set these two things equal to each other, notice that our velocities we don't have to worry about. So now we can get rid of mass on this side and mass on this side. Now we have 1/2 of 25 squared is equal to, and now our u here we said was 0.84 times 10 times the distance. Look, we've got the same thing on this side. 1/2 of 25 squared is equal to 0.84 times 10 times the distance. Because they're the same, we really don't even need to solve for d. We see that d on this side should be equal to the distance on this side. And it's because the mass here does not matter. So when we think about the mass right here, the masses, because the masses are the same on both sides of the energy equation, we don't have to worry about them. And when you skid, you go the same amount of distance. For page number 4, which is the next one, this one is just the definition of work. We know work is FD times the cosine of the angle. We also said that if the angle is 90, we could say F parallel to the distance, and we also know that that is equal to the change in energy. You must have a force and you must have a distance. Otherwise, you won't do any work. The angle cannot be 90 degrees, and why can't it be perpendicular? Because the cosine of 90 degrees is equal to 0. If your angle is 0 degrees, the cosine of 0 is equal to 1, so we know that this is positive work. If it's 180 degrees, you'll see they're both going in opposite directions, and the cosine of 180 is equal to -1, which is negative work. And then the cosine of 90 degrees is equal to 0, so there is no work done there at all. There's a special case, we've talked about this one in class a little bit, but if you carry a tray across the room at a constant height, there is no work done when you're carrying that tray across the room. Work is done when you lift or set it down because you're going either with or against gravity, and that's what you'll see. When we look at the pendulum, the work done by the tension force is actually 0. So if you think about the force due to tension here, because it is at a 90-degree angle with the velocity, which means it's at a 90-degree angle at any certain point with the direction, then you won't have anything there, okay, in terms of work done. So the work done by tension force is 0 because we are at a 90-degree angle. Work in kinetic energy chart, so this just will help you a little bit for a definition. If there's work done on an object, so for example, if I push a car, okay, then the kinetic energy of the car increases, and if it increases, so now we've got an increase in delta E, which means we have an increase in work. If I push on a car but I stop the car, so I use the brakes on a car. If I use the brakes, then I remove energy. So I'm removing energy by slowing the car. And if you think about it, 1/2 mv squared final minus 1/2 mv squared original. Since this is smaller than this one, I'm making the whole thing smaller. So I'm removing energy, which means my work is negative, and the kinetic energy decreases. Let's go ahead and take a look at the next page. This one deals with force versus position graphs, so we're going back to trying to figure out what K is again. So this is just a super important thing for you to be able to do. Notice that I have a graph here, you have the same one, and it wants to know what is the spring constant for the above graph. So the spring constant, remember, is the slope of this line. The good thing for you is all the dots here are actually right on top of that line. So we want to do the change in the force over the change in the position. And remember, that's equal to K because F is equal to Kx. So now we're going to take the change in force, let's do 100, and we're going to divide that by 0.03. And if you divide those two, you should end up with a K value of somewhere around 333.333 infinity, so we'll just call it 3,333 newtons per meter. So that would be the spring constant for this graph. Next page, this one is all about the area under the curve. So we still have our line here where we have our K value, but now if we find the area under the curve, remember that is looking at the work, or we're looking at the change in energy. So we're actually taking the force and we're multiplying it times the displacement instead of dividing it. Our unit would be a Newton times a meter, and that is the change in area or the work. Let's take a look at this graph again, and this time they want us to find the change in energy of the spring. We can't just start with this point, so we can't find the slope again. In order to find the work done, we need the entire area of this whole triangle. So to do that, we need to do the area of the triangle, which is the work or the potential energy of the spring, is equal to 1/2 of the base, and here we see the base is 0.09, and then we need to measure the height, and the height is 300. So I'm going to do that math now. I'm going to take 1/2 times 0.09 times 300, and I end up with 13.5 joules. Now it wants us to use both the area and the equation method. So let's use the equation method. If you remember from before, the spring energy is equal to 1/2 kx squared. We solved for the K earlier. We said it was 3,333, and then our stretch here is 0.09, and we need to square it. So we're going to do 1/2 of 3,333, and then we're going to multiply that times 0.09 squared, and we end up with 13.49865, which rounds us up to 13.5 joules. So either way, you should get very similar answers. One way you just found the area of the triangle, and in this one, we actually found using the spring constant. So you have to find the spring constant first, like we did on the other page. Let's go ahead and take a look at the next page. So this one's just about work. We know that work is, it's about power. Power is work over time. And so one of the equations we use for power is W over T. We know the unit is a joule over a second, and that's a watt. We could also have it as a Newton times a meter over a second. And so here's what we're going to do. P is also equal to force times velocity. So here's that force times velocity. Once again, the force and the velocity, if they are at 90 degrees, there is no power, all right? Notice the units is a Newton times a meter per second. The sign of work due to gravity, when you stand up, you work against gravity, so the work done by gravity is negative. When you fall down, you work with gravity, so the work done by gravity is positive. So it is okay to fall. That makes it positive. For the next two pages, all we're going to do here is look at work done by conservative forces. This is where the path doesn't really make any difference, and we can calculate the work with the starting and the ending points only. So the actual path is ignored. If you carry a box up one flight of stairs and your friend carries it up 3 and then down 2, you end up at the same level. You both technically did the same amount of work. Work along a closed path is 0, so if you start and end at the same spot, then no work is done by the force. Work does change potential energy, so examples would be gravity and the spring force. If we look at the bottom of this one, we're looking at this picture from the side. So this is a box. It was pushed along, it was picked up just a little bit here. It goes to point B, it's lifted to C, it goes back over here to D, back down to A, and then it's finally set back down where it was here. They want to know how much work is done here, and the cool thing about this is the work here is equal to 0 joules, and it's because this is a conservative force, and I started and stopped at the same place. So there's no work to go left and right. You'll see that right here. The work is negative going up. Then the work going from here to here is 0 again because you're not working against gravity. And then when you let it down, the work here is positive. So these two are equal and opposite and cancel, and therefore we don't have any work done at all. The other way you can think about this is to write this out. So we would have the work going from A to B plus the work going from B to C plus the work going from C to D, from C to D, plus the work going from D over to A, and that would be our total work. So from A to B we said was 0, from B to C is negative. Here we've got 2 kilograms times 3, and then we plus 0, and then this is plus, and again we have 2 times 3, and notice I forgot the 10 here, so we'll put that in. But if you take 60 negative plus 60 positive, you get 0 joules. And so that's a little bit more work for you to be able to see. For the very last page, this one's pretty simple too. This one is non-conservative forces where the path is dependent. So if you just know the starting and end points, that's not sufficient to calculate work. Work along a closed path is not 0. Work changes the energy. So here if you have friction or air resistance, then you've got to use non-conservative forces for your work. If we look at this picture, we are losing energy in the form of heat. I took the box and I slid it on the floor from A to B. So you'll notice there's an equation here that shows that work is negative mu K times mgd. So this is just friction times the force of friction times distance. So this is just work is equal to negative force of friction times our distance. And it's negative because it's opposing our motion. They want to know if I go all the way around from A to B to C to D and then back to A, they want to know what is the amount of work that's done. So this one we're going to get a value. So the total work here is the same thing we did before, work A to B plus work to C plus work done from C to D plus work done from D back to A. So I'm going to do each one of these. Notice that our equation here for A to B is negative mu K, that's our coefficient, times m times g times the distance. So let's do this first one. Mu K, we're going to do negative 0.2 times our mass, which is 2, times 10 for gravity. And if I multiply that times 10, and then our distance is 3 meters. I'm going to do that 4 times, 1, 2, 3, 4. So really I can just take this thing and I can multiply it times 4. So I'm going to do that. I'm going to take 0.2 times 2 times 10 times 3, and then I'm going to multiply that result times 4, and I end up with negative 48 joules of work. Okay, that is work done on the box because it is opposing the box's motion. I would do 48 joules of work to push that box in that path. And that is the end of the multiple choice review.